Yes, you can see.
Okay, thank you. Okay, so last week we stopped at we stop at trying to make some quantitative summary while we talk about the mean, the median, and the mode. So we're trying to use table one. Yeah, there is a package called table one. Yeah, table one. We're trying to use that additional package to create some quantitative summary. That was where we stopped. I think we stopped at this, yeah, particular point. So where we have to we need we have two variables called height one, height and height two, and we're trying to make height one to display the mean and the standard deviation, and height two should to display the median and the interquartile range. So the difference between these two quantitative summaries is that one is follows like a normal distribution. When your data is normally distributed, the quantitative summaries that is attributed for that kind of data is mean and standard deviation. You just have to report your mean, which is measure of central tendencies, and the standard deviation, which is measure of spread. And if you have height two, if you have height the second height, maybe that is somehow skewed, maybe to the right or to the left, it is better to report the median and the interquartile range, because the median is not sensitive to outliers. So that's why we're trying to practice this during the last class. So now I'm going to start from this place. So now um, so if you have one categorical variable, and you have one categorical variable, and you want to be sure, that, oh, okay, this variable is actually categorical. One thing you have to do is that, when you try to import your data, you need to check the structure of your data using the function called str and ht. Yeah, that's the name of the data we were working with last week. So from this place, you can see a quick attribute of your data, like the structure, the first some of the first few observations. So if we go to height 100 underscore character, you're going to see that this is character. Once you look at height 100, height gt 100, I don't know, it's from the height data set. We are going to see that this data recognize height GT100 as numeric, because it consists of 0, 1, 0, 1, 0, 1. But it recognizes height GT character as character type. Why? Because I've run this earlier before the class, so I have it saved on my computer, on my hard environment. So what you have to do is that you have to try to use ht then dollar sign to create a new variable called height gt100. So you have to use ht then dollar sign, you write height gt100 underscore chr, which stand for character. Then, because ideally this data might not have incoming. Let me try to remove this data so that you can see what I'm saying. Okay. So, mm, 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 Mhm. Sorry, everyone. So if you check the structure of I really like imported the data. If you check the structure of HT, right? So we are going to see that in this variable now, when I like reload the data, we don't have this variable called height gt 100 underscore character. So what we want to do is that we want to create a new variable called igt 100 underscore character and treat it as a character type of data, that is a qualitative type of data. Because now if you check the structure, you are going to see numeric. The igt 100 that we have there is 0101, which denotes something, but the but R does not recognize that as a character type of data. So now, how do we change this numeric data into character? That's what I'm trying to like talk about. So you have to assign it to, you use the function called as character. Then you pass the variable you are trying to like convert to a character type of data, which is height, okay, ht dollar sign height gt100. So once you run this line of code, check the structure again, you are going to see that automatically it's going to create a new variable and convert that character variable type to character type of data, which is 01010101. And you can see here that it gives attributes to the data point. So you can now use your table one, like specify your vars, which are your variables the variables you want to actually summarize. You want to summarize, so which is height 100 and height 100 character, right? Height gt 100 and height gt 100 character, right? So you create a table one function where you specify your vars to be vars, which is this. Your structure, yeah, we don't have structure in this case because we don't want to group them by any other variable. What is your data, the data you're working with? You're working with height, and if you wanted to include any, you put true, but most likely you have to like put false. So once you write this line of code, then you summarize. You are going to have two outputs, yeah, kind of two outputs in a output. So some summary of quantitative variable. So this is just the height GT, which R does not recognize this as a numeric, which R recognizes as a numeric data. We are going to have the number of the number of samples, the percentage of missing, which is 00. You have the mean, you have the standard deviation, you have the median, you have the 25 percentile, you have the 75 percentile, you have the mean, you have the maximum, you have the minimum, you have the maximum, you have the skewness and kurtosis. So why summary of the other one, you are going to have the summary of the other one. Can you see summary of categorical variable? You are going to have the number of observation. You are going to have the percentage, the number of missingness. You are going to have the percentage of missing values. You are going to have the levels. You know, we have 0 and 1. Is 0 denote something and 1 denote something? Maybe we use a cutoff mark of like, let me just say 50, and we said any persons of greater height, of lesser height than 50 is let's just say is short, and someone greater than 50 is tall, kind of. So this gives like okay, 0, how many people are short? This 51 frequency, and percentage is 54.2% of the patients are short. Why? It's going to give you two levels, because we have two levels in data, that's 0 and 1. Assuming 0 is short and 1 is tall. So this gives information about the data points when they are in character type, like in frequency, percentage, and cumulative frequency. So that's that. So we have these following questions to answer actually. So using the I think resident doctors, yeah, resident doctors resident doctor data. So before I continue, do you have any question regarding what I just explained now? Okay, I'm going to take that for no, right? So okay, just in case you have any question, I don't have access to like to see who is raising up their hands and all this kind of stuff. So you can just like unmute and just ask any question you have maybe in between the section. So now we have this data set we want to like work with. So we need to download the resident data, which I believe everybody have the resident data. We want to like estimate the GHQ score and the GHQ sum score. We want to estimate the 25% and 75% percentile of job satisfaction score and the sum. We want to like check what is the maximum job satisfaction score, how many female residents are there like are there in the observation in the data set. We want to check the age distribution of the resident doctors and how many female doctors are younger than 30. Those are the questions we want to answer actually. So you start by like importing your data set. So using the read.csv because I have the data set in CSV actually. So you check the head, which is going to give you a default the forces observation using the head function, right? So when you use the head function, you see the forces observation and see like how the data structure looks like, how the first 6 observation looks like. So that can give you like a whole lot of information about that. So use the function called str. You pass str into your data name, which you see by data as RDS, right? So you are going to have these structures. The structure. I would like tell you to like if you have your R open, you should walk through this problem because yeah, you should walk through this problem because while I was walking through this problem, I changed some variables because there are some variables in the R markdown maybe that was not like in the data set. So we have to like work with what we have in the data set. So we have to like do some 1 or 2 changes. So now we want to check the structure. So this is the structure of the data set. You see age, numeric. You see mental health score, numeric. You see job score, numeric. Workload score. You see them to be numeric. You see H cat, which is H category. You see them to be character type. Mental marital sex, character type. We have children. That's numeric. Female, yeah. So this represents maybe 0 to like to be male and 1 to be female. So yeah, so this is numeric. But if you want to like count this, if you want to count them, like you want to count how many female do we have, how many male do we have, you have to like force this data. Like, you're not forcing, you have to change this data type to character type of data. So now we have hours worked, which is numeric, and married, like marital status. This marital status is how many of them are married. Like if one can say yes, 1 can represent yes, and 0 can represent no. So that's what we are trying to estimate. So now I said you have to work this problem because if you use names of RDS, you are going to see that among these names of RDS, we did not have any variable called GHQ score underscore sum. We did not have it. So, and what we are trying to do is that we are trying to like measure the mean, we are trying to like mention the mean GH score, which is not like included in the is not in the data set. So now we have to change that to like be okay. Let's estimate the average job satisfaction score or mental score. So we have to like change this from this sum to let's just change it to mental score. So estimating the mean mental score. So it's out of the observation, I think, well, how many observation? 161 on the observation. The mean of the mental score mental score among the resident doctors is 23.68, which is approximately 24. Yeah, which is approximately 24. So this tells you the mean values. So now we want to like estimate the estimate the 25% percentile and 75% percentile of the job satisfaction, right? So we still use our package called table one. We use our package called table one actually. So once you use you have to specify the variable which you want to like work with, which our variable in this sense is job satisfaction, right? So we use the function called create table one, which takes an argument of vars, which represents the variable you are working with. Structure. We are not stratifying this by any group at all. We don't want to see package of like job satisfaction within the male and the female. No, we don't want to see that. So the data we are working with is RDS. Should this summary include NA? That's missing observation. We said first. We just want to see the actual observation without so I made mention of something regarding the variable's name in the observation. So we don't, if you check back the names of the observations we have, we don't check the names of the variables we have. We don't have jobs satisfaction sum. So definitely this should be score. So once you run this particular line, you are going to have.
Can I interrupt you?
Okay.
Yes, I'm not able to load table one. I just want to know if I'm getting like, is it just table one? Because I can't see what you have written, but you said I can see library in brackets. I want to know, is it spelled TABLEONA?
Yes, exactly.
Okay, I'm not able to download it.
Can you share your screen?
Yes, please.
Okay, yeah. So I think you can share your screen.
So this is what I get.
Okay, can you load that line 12? Let's see what up.
Sorry,
Okay.
I have a question.
Oh,
what file are you using? What file is this?
There is no package called this is our lab 2 that we were working with the last class.
Lab 2, okay.
So you have to like write install.packages. Open brackets. So double quotes. Then type table one.
Please, can you show me? I feel lost now. I don't know if you can also guide me.
Okay, seems to be working. Thank you.
So now you can
let me share my screen, please. I'm lost.
Okay.
Okay, so okay, yeah. So this is my arrow. This I don't know, like
okay. Can you exit this this interface? This is R itself. This is the interface, so you might get confused. Yeah, actually,
okay.
Yeah, just exit this. So just search Out Studio on your search.
Okay.
Yep. So this is
okay. So that thing is another one.
That's our interface itself.
Okay. Yeah. Okay, so I'm here now. Okay, so what document am I using?
So our lab 2. Can you see from this?
Okay, I'm seeing it.
Yeah, you are in our lab 2 already, so you can just go down Go down.
Mm-hmm.
I think so. Go down. Just go down. Go down to locate where we are actually. So we are trying to like attempt some questions. Yeah, this place. Yeah. From line 130 downward. We are trying to like attempt some questions.
Okay.
Yeah, so you can see some questions in the. Is it possible to increase? Oh, okay. The size I can barely see. Sorry, Steve. I'm just saying this question. Please, is there any function to undo in R? For example, I think there is a function to undo in R actually. I'm coming. Let me see because
Mm.
well, it depends on what you are using actually. I think Control Z should undo if you are using
What should I undo? What am I supposed to undo
no,
here?
not you. I'm attempting to. I'm answering to someone's question in the chat box. I think
Oh,
you
okay.
should like undo if you are using if you are using if you are using Windows and Control Command Z should like undo if you are using Mac. So we are trying to answer these questions. So you can load um from 141
How do
141.
I load it? How do I load it?
No, go to 100 line 141.
Okay.
Load the
Oh,
attribute. Yes, exactly. But you are going to have, I think you are going to hit an error. You know why you are going to hit an error is that
okay.
you just what are you calling it? Clean from I believe you must have your data now. So clean from resident backward, like is it backward? Yeah. Left resident, no, go down line 141. So
Mm.
do you see that RDS, right?
That three dot. Mm.
No, not that three dots, not that three dots. Go to 14143.
Okay. Idea.
So now wait, don't clean. Just go to if you read between lines, you are going to see start 101, right?
Starts 101.
So click on start one, move forward again, just once, move forward once, not backward, forward, starting from that R, starting from residence. No, after that start 101, that residence, that from that R.
Mm-hmm.
So clean backward up to that C, not the resident doctor. Like no, backward up to the C,
Mm-hmm.
not start cleaning the first C that has that semicolon.
Mm-hmm.
Don't clean that quote.
Mm-hmm.
So you can clean just backspace. So run this line, let's see what happened.
Mm.
So you have your
Okay.
data set now. So
Mm. Okay. So what next?
so now you can start running the lines of code as like I walk everybody through just so this is just checking the heads, which is going to give you the first 6 observation at default. So once you go to the next line, to the next chunk, it's going to give you the structure.
Okay.
Go to the next line again. So I was saying something about the variable names. We are trying to okay, this works. Yeah, nice one. Job some. So yeah, so
Mm-hmm.
yeah, so that's where we are now.
Mm-hmm. Okay.
Yeah. So I mean, is it that you need to yeah, you need to like impute, you need to like load table 1 to be able to like have access to this like function. You don't necessarily need table 1 to like check to calculate percentile because I think there is a function called IQR now. Let's try that. But why we use table 1 is that share screen. So someone was asking if I could zoom. out. I think this is more preferable, right? Okay. So there is a function in R called coming IQR, I think so. IQR, yeah. So if you have your IQR and you like pass your job HT $ job satisfaction. Are you working with HT? No, RDS, sorry. RDS $ job satisfaction. Coming C, I want to see 0.25 and 0.75. Okay. Props. Come in. I need to check this. Compute intercultural range. Okay, this compute intercultural range. There is a function. Yeah, I think there is a function for that. Let's see what this does. Okay, yeah. So there is a function to like calculate percentile, which is called quantize. So what quantile? You just pass your variable of interest. Yeah, and this props acts like it's just like asking you what percentile you want, what quantile you want to calculate. Is it the 25%? Is it 75%? Is it the 50%? Yeah. So if I claim this and just pass only this, it's going to calculate like the 5 quantile summaries, the 0%, 25%, 50%, 75%, and 100%. So for you to now calculate the interquartile range, I think there is a formula for interquartile range. So I think this works for interquartile range. Just pass your RDS, then yeah, I think this works better actually. So your interquartile range, but this is just going to give you your interquartile range actually, but this gives you your percentile. So this gives you your percentile. So yeah, but we are using this table one to like create summaries of what happened in the data set. It's going to give you the number of missing, the mean, the median, the standard deviation, and all those kind of stuff like that, the maximum, minimum, and all this kind of stuff like that. So now we want to like, what is the maximum job satisfaction score? So, and we want to like from this place, from this summary, after creating table one, you can see the maximum. What is the maximum? The maximum is simply 13. So if you don't want to go that route, you can just use max function, then you pass your job, okay, your RDS $ job satisfaction, job satisfaction. So you're going to see that the maximum is 13. So that's the maximum. That's the maximum we've gotten. So that table one is just like, it's just helping you to simplify your work and make it much more simpler. So how many doctors, like how many female resident doctors are like at the end of the observation? How many like female resident doctors? You know, in an hospital you have like male resident doctors and you have female resident doctors, right? So we want to like check, once you run this like this line of code, we are trying to check the type of variable, like not okay, the type of variables, like the type of variables, that particular variables, the type of, what is the type of that variable, which the type of variable we have, like we have called female in that observation, in that data set is called is double. So we have to like convert it from double to character, because it's a character type of data once you want to count. Once you check the structure, I'm coming the structure of RDS, can you see this female is reading as numeric? Once you want to count something, we want to count this. We are not like trying to like how will I say it? We are not trying to like check the average. This, you cannot check the average of a count data. Just like yes or no, yes or no, yes or no. I want to check the average of yes or no. No, you can only check the percentage and the frequency. Yeah, you can check the distribution at which the ratio from male to female, the distribution from male to female and all this kind of stuff. So we have to like change this data set, this data structure, this variable structure to be character type of data, qualitative, so that we can count. So that we can count. So now we have to like create a new variable called female X. So if you want to create new variable, the easiest way to create new variable is that you have to like RDS, the name of the data you're working with, then $sign, then you specify the name of the new variable. So female, we want female X, right? So you treat female X as character type of data of RDS female, because we have this RDS this female variable in the observation. What we just want to do is that we want to like change it from a numerical structure of data to like a qualitative data. That's character, that's like quantitative, qualitative, where you can like try to like check the frequencies. So now once you run this line of code, you use your table 1. We use the package in table 1, but something about this table 1 that comes often. Once you've already load your table 1 earlier in your document, you don't have to like keep doing it. You don't have to keep doing it. No, you don't have to, once you've load that table 1, you've trying to like you've import the library while working immediately in R. You don't have to keep reporting. You don't have to keep loading it often and often. So we specify our variable, which is variable X. Our create table 1 takes variables, takes structure, strict data, and do you want to include any, which is false. So once you summarize this, we are going to have the levels, which is 0 to be male and 1 to be female, right? So you can see the distribution that 68.3% of the resident doctors are male, while 31.7% are female. So that's what this does. So once you want to check what is the distributions, like you want to check the distributions of the resident doctors, please be sure to like know the kind of variables, the variables that are in the variable names in your data set actually. Because I ran this code earlier, so I was able to detect from my own end each distribution is H category. Is mentioned as its category, which when I check type of, I'm asking what type of data is it? What type of data structure is this? Is it numeric? Is it integers? Is it character? Which R2 tells me that each category in my sense is a character type of data. So we have to like, so this is already in character, so we don't have to like convert, we don't have to convert this into we don't have to convert it into what are you calling it, into character type. It's already in character type. So what you have to just do is just like save the H category as a vars, it cards as vars. Then you create table 1, right? Once you create table 1, so what we want to see now is that we want to see H categories of female doctors. That's what we are interested in seeing. That was why we specified in this tractor C as a female doctor, like female doctor X. If you check this tractor earlier before this, we have not been like using this tractor. Tractor is like a grouping factors, a grouping variables. You want to like group a particular variable by another variable. So now we want to check the H categories of the residents doctor, but female. That's what we are interested in doing. So it's going to ask you the data you're working with, which is RDS. It asks, do you want to like include any, which is false. So once you run this line of code and you push summary, you are going to see their age distribution, like the age distribution. So this is female, like the female observation, like these are female in the data set. So you're going to see from age 25 to 29, we have 9.1%. That is 9.1% of female residents are within the age of 25 to 29 years, while 41.8% percent of the of female female residents falls within 30 to 34 age bracket. So and so on, and you notice that up to the end you have 1.8 percent of female residents falls within 50 to 54. So this can help you to make like quick decisions as stakeholders, that as the age increases, the number of female residents we have within the medical facilities reduces. Yeah, and you notice that at a let me just at a mid age, we have number of female residents that work we have number of female residents that are actually much than the earlier age and the late phase, the late phase, right? You can make all this kind of observation. This can help you to like maybe check what is happening, how many people like get out of the job after some certain age and all this kind of stuff like that. So and it's going to also like try to like create another coming. So it's going to create a variable another section for male, because if okay, let's say if 0 represents, let's say if 0 represents male, right? This observation is regarding male, this information is regarding male. And if 1 represents female, so you can interpret this with respect to female, and you can interpret this with respect to male. So you just have to know how your data is being coded, like how your variable is coded. It's 0 for male and 1 for female. It's 1 for female and 0 for male. Like it's 0 for female and 1 for male. You have to know what your observation entails. Like is this 0? Like you have to know the coding for you to be able to interpret this kind of table. If 0 represents male, then this summary, this quantitative summary is for male. And if 1 represents female, this quantitative summary is for female. So so now we move to visualization. Before I start visualization, I don't know, do you have any question? Because that's the problem we have in that observation, and we've solved the problem already. Any question before I continue? Okay, you can unmute yourself.
I'm sorry, I'm stuck in the number 2 question of the classwork. I don't know if I can share my screen. I think there may be an issue with the code I typed.
Yeah, you can share your screen.
Okay, thank you.
So someone is asking, can anyone share me the data sets we are working with? Okay, the data set is in the Google Classroom. The present one we are working with is the height data. We are working with the resident doctor data, and subsequently we're working with the ion and GP trial data. So I think you can get that from the Google Classroom. Okay, you can share your screen, please.
Okay, I'm sorry.
We can't see your screen yet.
I'm sorry. I think my system is asking me to do something in sentence, which will take a bit of time. So maybe I'll just allow other people to go on, and then maybe later I can press share. Thank you so much. Sorry for this.
No, it's fine. It's fine. So, okay, is there anybody with any question again? Because before we continue. Okay. I'm going to take that as no. So now we want to talk about visualization actually. So, and this will be working with the height data actually. So we've previously loaded our height data earlier. So we've loaded height data earlier. So now, you know, we have different okay. Can you speak?
I
I
have
can.
a question, yeah, about my histogram. I tried to do the histogram, but it's not doing. I don't know if I can get some help.
Okay. Can you just chew a little bit to maybe
Okay.
run the line of code? Then if you still have the same problem, we can trash that out.
All right.
Yeah. So we have different kind of histogram, right? We have different kind of histogram. No, sorry. We have this different kind of visualizations and techniques, and we have different kind of plot. So you need to know like what you are trying to like get, like, okay, because when you have like one single numeric variable, there are some suitable plots for that. When you have two numerical variables, there are suitable plots for that. When you have one categorical variable against a character type of data, you have visualizations for that. When you have two, let me say, when you have two character type of data, let me just say you have marital twos against age bracket, their character type of data. So you need to know how am I you need to know the type of data you have and the type of question you're trying to answer, because the type of data you have we actually tells you the kind of visualization you are going to use, the kind of plot you are going to use. I can't just come and plot I can't just come and plot, what are they calling it? Come and plot a box, no, a bar plot for like two numerical variables. It doesn't work that way. It doesn't work that way. So we have to, like, this section now we are moving to, we have to talk about visualization and what visualization is good for what variable, what visualization is good for these variables, and when you have like multiple variables, how can you work them through. So now we are using our height data, so which is saved at my own end as HT. I think in your own R Markdown lab 22 is saved as HT, right? So once you check the names of the observation of the variables in height data, right? HT. Once you check the names, we are going to see we have ID numbers, we have heights, we have height 2, we have height 100, and height character, right? So now we want to like check the histogram. What histogram does is that once you like histogram of height, this is what like it's going to like is we use the function called is is hist HIST. So then you pass your HT, which is the name of your data, and the variable you are trying to plot, which is this. So what the histogram does is that it gives you the distribution of a numerical type of data. Let me say continuous data. It gives you the distribution. Yeah, it gives you the distribution. So these are the distribution against the frequency. So from this histogram, you can see if your data is normally distributed, and you can see the behavior of the data actually. So you can see the behavior of the data. So if you've tried this and it's not working at your end, can you just let me know now if it's not working at your end, so that we can see what is happening, and that will not disrupt subsequent line of code. So I believe this is working like at everybody's end. Like,
Please, can I ask, did you read in a different data set? Because I'm not seeing height in the resident documents.
No, like the data set we are using now is height data set.
Oh, okay, thank you.
Yeah, so I think you just have to load height. It is called height data set. But if you check the R lab 2, it is load as HT. So I think we've loaded that previously before like getting to this part of the line, to this line of code. Okay. So this is going to like give you a distribution, like distributional behavior of your height data set. From this place, you can see, you can make some inferences. Is it skewed? Is it not skewed? all those kind of questions like that. As you can see, this likely looks like a normal curve, like in a normal distribution. Yeah, but visualization alone cannot tell you if something is normally distributed or not. Actually, yeah. So we can move forward actually. So when you have two numeric variable, okay, I want us to check this stuff. Okay, now let's check the structure. Sorry, let's check the structure of RDS. We are using both RDS and what I call it. We are using both RDS and height data set. So now, if you check this RDS, you're going to see workload score, right? Okay, let's change. Okay, let's pick what let's pick workload score and children, the number of children the resident doctors have, right? So let's do workload score and children. Once you plot this, these are two numerical variables. So this, like, if you want to plot two numerical variables, when I mean numerical, two quantitative variables, you use like a kind of scatter diagram. Use scatter diagram? So it's just that you want to check the relationship, like what happens if the number of children they have increases, what happens to their job, to their workload? Does it increases or decreases? That's the kind of question you're trying to answer. So use the function called plot. So once you use plot, it takes x and it takes y. So our x equals, in this case, equals RDS, because we are working with RDS, right? RDS $ mental score, right? And our y represents RDS $ children. So I'm coming. Okay, I use small letter. I'm using capital letter, right? Children. Yep. So yeah. So you're going to see the distribution, and you'll be able to like make decision of what happened if what happened as the number of children increases, what happened to the to their workload. You can check between workload and job satisfaction too as well. Let's say plot x equals workload equals RDS $ workload scores, and y equals RDS job satisfaction. So you can see what happened to within workload and job satisfaction. You can check. This can give you brief correlation between two numerical variables or what happened. So that's that. So this package, this plot function we are using, and this histogram function we are using now, these are base R function. So what happens if you want to like customize your graph? You want to make it looks more eye friendly, you want to make it looks more color friendly and much more interesting. So that is where this comes in. We have a package called ggplot2. Yeah, ggplot2. So this is a package called ggplot2. So you have to like install packages ggplot2, then you load ggplot2. And we are working with the height data set, the height data set. So is anybody with question? Do you have question? Okay, so I can continue, right? So okay. So now, how did ggplot2? How does ggplot2 work? So previously we have been using plot, right? So ggplot2 use it has a particular kind of structure. First one is, it's called every structure, every function in ggplot. Like when it comes to plotting graph, making graph, you have to start with ggplot first, which this ideally start for your plot. ggplot. So ggplot is going to ask you, okay, ggplot, what did I want to plot? Okay, from what data, like which data am I working with? So you have to specify your data first. Once you specify your data, in your data, you're working with variables actually. You are not just working with mere data alone. So you have to specify your variables, which is X and Y, right? But you have to specify this into AES. It's called statistics. Is it statistics? Yeah, statistics. This is called statistics. It's called AES. So instead of when we were plotting from the base, we use plot X and Y. But this is passed into the AES function. AES argument in the ggplot. So first thing it takes your data, the name of the data you're working with. Second thing it takes your X and Y, which is passed in the AES, right? Your X equals comma and your Y equals comma. So plus, you have to add plus. So now, because we have different kind of graphs, we have the bar, we have the column charts, we have the scatter plots, we have the violin plots, we have many type of charts, many to even come. So we have the box plots, we have the like a whole lot. So what you want to do is that you want to specify what type of plot are you talking about? What type of graph are you talking about? So if you want to specify the kind of graph you're talking about, it takes geom. Once you use geom underscore, you are going to see the list, the list of type of graphs ggplot has. It has density, it has hexagon, it has h-line, juncta, labels, range, and so on and so forth, like that. Polygon, a whole lot. So you have to say if you are working with histogram, it's going to ask the GG histogram. Then you pass the what I call, you can just click OK. Then it's going to plot GG histogram. So let's fill this up and see what happened. So now we are working with HT data, right? That's it. We specify ggplot our HT data. What's our X? Because histogram only takes X value. Histogram does not take Y value. So height, right? Once you plot this, you are going to have something like this. So this is your histogram for that height variable in the data set. So this works for every other chart type, maybe geoplot, box plot, and all this kind of stuff. You just have to know the set of arguments that thing takes. Once you write geom underscore plot box, you have your box plot geom underscore bar, you have your bar plot, and so on and so forth. So you have to know the type of variable you're having and what type of chart type, what type of graph works for that variable. So that's it. So now, but first thing first, how ggplot works, you have to use ggplot first, then you add the kind of plot, the kind of chart you are trying to plot. Is it bar, is it chart, is it column, is it density, and all this kind of stuff like that. So now, if you check this example that was made in our R lab 2, right? So we've already saved ggplot data which is HT, and our AES, which is we are specifying what data points, what variable we want to plot in HT, in height data, which is height, right? We've already saved it to be P, right? So we now come to the next line of code. We now say P plus. Previously I specified that I used plus here, but the difference between this first thing I did and this second one is that we've already written this into a name called P, into an object name called P. So that's the difference. Nothing different, nothing significant. It's just that's just the difference between what I've done up there and what is on line 302. So now you have to use P plus. What do we want? We want histogram, right? So we are not trying we are trying to put some fancy, when you have okay, now I want to go out, I wear a sunshade, put an hat, wear a wristwatch, all those kind of stuff like that. We are trying to put more fancy, add more, make it more eye friendly and more colorful. That's what we are just trying to do. So fill, we use the fill, we set fill to be black. Okay, let's try to like explore this and see what happens. Fill equals black. So you can see what happens when fill is set to be black, right? So sorry, it's fill, not fill. Yeah, okay. When you specify your fill to be black, can you see what happened? It changes the color from like kind of gray, like deep gray. Is it deep gray? I don't know. Yeah, I think it's deep gray into a black color. If you change the fill to be red, you see what happens. Yeah, this happens when you change it to red. I might not be able to like talk about all this fill color and color in subsequent like lines. That's why I'm taking my time to like explain what each does. Okay, when you specify color, let's see what happened. If you specify color to be red, to be black, let's see what happened. Black, right? We are going to see that at the tip of that bars, you have black color. At the tip, you have black colors. So now, what happens if I set alpha equals 0.25? So you're going to say that it's lightening the red colors, like it's kind of, how would I put it? It's kind of make it more transparent, like transparency. That alpha gives you like transparency. I don't want it to be deep, like the graph to be very dark. So I want it to be kind of transparent, that you can even see the line, what are they calling the major lines? You can see the major lines. So now, what else? What else? You can put bandwidth. Is it okay? Okay, bin width, right? Let's put bin width and see what happens. To be 2 equals to, let's change it to 4 and let's see what happens. I think that should show what will happen. Let's change it to 5 and 6. Can you see? As you increases the bin width, the bars increases. The bars increases. Once you decrease it to, it decreases. Let's change it to like 0.5. Let's see what happens. So can you see? You have many of it, depending on how you want it to behave. So now there is something we call labels. You want to add labels. You know, I can't just like give this visualization out to an average layman and expect this layman to like explain what happens in this graph, because it has no title, it has no y-axis attribute, it has no x attribute. So what we are going to do is that we are going to use the function called labs. It's called labs. Labs. It takes set of argument of title, histogram, right? Comma, y-axis to be frequency, and finally x-axis to be what? X-axis to be height of kids in clinic, right? In clinic. So yeah. So now you see the title, it shows the title right over here. It changes the frequency, like the frequency we are trying to, like the variable we are trying to measure. We are measuring the height of the kids against the against frequency, like the height of the kids. Like we want to see their height at 80. How many children have 80 height of 80? 100, how many children have 100, and all this kind of stuff like that. So that's what we are trying to. So that's how ggplot works. So over here, what we are just doing is just that after we specify, we've written our ggplot, the name of the data set and the observation we are working with. We've written it into object called P. We're just adding plus. We're just adding the statistics, like what type of chart am I trying to plot? Yes, we put the statistics to make it more beautiful. Labs, putting the lab so that anybody coming can see what goes in the data set. So before I continue, do anybody have any question? Okay, the question. Sure. Okay. So now, changing the appearance. Okay, now we have something we call teams. Yeah. So teams. Let me go back to that line of code we just work with. So now there are different kind of teams. So we have teams. Once you just type teams underscore, we have classic. Once you run classic, can you see what happened in classic? It changes the background of, like, is it the background? It changes the teams of the graph, like of the chart we are working with. We have team minimum. Yeah, I really love this actually. I use minimum a lot. So minimal. So we have minimal. We have, I think, team gray too. I think there is something like gray. Yeah, teams gray. So the default one is team gray. We have team gray too as well. We have different kind of team. Dark. I'm interested in using dark. We have team. What again? We have line draw. A whole lot of teams. So a whole lot of teams. Those are things you can explore at your own leisure time. At your leisure time. So that's what happens here. So what happens again? Okay, these are just like teams, trying to like add teams, which I've done. Okay. Now another question is, if we want to like add a vertical line to the histogram we've plotted. We want to add a vertical line to the histogram we've plotted already. So how do we do that? How do we add vertical line? So that is where GG, what are they calling it? GG. Let me run this line of code. This to this without running the vertical line. Without running the vertical line, you can see that we have a clean, what I call it, a clean histogram. The way we add it in the first when I was trying to like build this plot up, right? So now GG, but okay, you have to notice that every geom plot, every geom plot, let me just put it like that, every geom plot has its own function they take. When I mean geom plot, after using your GG plot, like all the other geom, histogram, geo v-line, geo labels, everybody have their own function they take. Like, so you have to be sure to know the set of argument they take before you can use them very well, very effective. So in this case, what does geom v-line does is that it creates a vertical line. We have geom h-line too that creates an horizontal line. So it creates a vertical line, yeah, with some certain set of arguments. That is, you are going to give a kind of, you want to like see what happened in the you want to see the middle values. You want to see the middle values of the children height. Yeah, you want to see where it spots and how it like separates the middle how the middle values separate the height of children into like groups. You want to see that kind of stuff. So let's assume that the middle value, let's assume that the mean is 99.74. Let's just assume that's it. So you have to specify x-intercept. It takes argument called x-intercept to be equals to this. So line type, we have different kind of type of line. We have dots, we have dash, I think so. We have dot. Those are the two I can remember. We have dot and dash. So color, just same way you specify color, and we want size. Okay, let's add this line of code to this. Let's add it to this. Can you see what happened? It creates like a dot line. You can do this too for what are they calling it? For vertical, for horizontal line. Let's add horizontal line. I'm coming. Each line, right? Each line. Post y intercept to be, let me just say it to be 7. Let me just say it to be 5.5 line type. Line type equals blue. Let's see what happened. So then I've missed one of the arguments. For this particular horizontal line, which you might check with what are they calling it? Question mark. So can you see it's create another horizontal line, right? So So you have to be sure which argument each geom takes for you to be able to like use it effectively, right? So now that's how geom line, horizontal and vertical line works actually. So now we want to like to give someone like, maybe I'm trying to like explain this red line to someone. I can't just give someone this line, like this graph like this, and makes it make sense. No, it doesn't make sense. It doesn't make sense. So now I will use geom label, like we want to label that red line, right? So we look at the spot at which it falls. Like I know I can label it at y-axis to be 12.5, and the my x-axis is 99.75, right? So if I add this line of code to this line, so you can see the label up here. Okay, I was saying something that, let's assume that's like the average height, right? Let's just write average height. So anybody coming automatically reading this visualization can know that, oh, this red line like shows average height. Oh, let's check to the left, let's check to the right, what has happened. So any question? Any question? Okay, no question. So now we are going to like density plot. So density is just like how will I explain density? It shows like the distribution too as well. Just like histogram, it takes every argument just as geom histogram. So let me just show density plot. Let me copy from this place so that we won't waste much of our time. Just copy from this place. Yeah. The only thing I will just do here is just to change this to like geom. Okay, density, right? Density. Yeah, density does not take bandwidth. So I'll be kind enough to like clean that. I'm coming. Fill color. Geom density. I'm coming. Oh, okay. Oh no. Let me be sure. Let me build this from scratch and see what happened. HT AS plus X plus height plus geom density. Okay, yeah. If I run this, the way we were trying to like build our histogram, height, AST, statistics, x equals height, right, and density. This is what you are going to have. This is what we are going to have. So this order, okay, let me add labels. Let me just add labels. Let me add labels. Oh, okay, like I see the problem now. Oh yeah, I see the problem we are trying to. I'm facing the other time. Yeah, I see the problem now. So when I add this, let me add this as statistics to it. Fill equals black. I want color equals blue. And I want alpha, that is transparency, kind of transparency stuff, to be equals to 0.5. Let's see what happened. This is what happened. Yeah, this is what happened. So I can now add my labels like labs. I want title equals density plots. I want x to be this, y to be this. So it's going to show. So it's just same pattern. It's just same pattern, same ways, nothing different, same way. So any question? Okay, no question. So now we have bus plots. So we have bus plots. So what does bus plots like? What does bus plots does is that they are used to identify outliers and also distribution of the data actually. So RDS, we must be very sure of the variable names we have in our RDS data to know. Do we have we have age. So now we want to check if you use the normal base R, right? The normal base R, this is what you are going to have. If you just pass bus plots, RDS each, that is, you are specifying the variables in RDF, and you want your Y labs, that is your Y axis to be each in years, and your X axis to be all. So this is what you are going to have. This is what you are going to have. This is what you are going to have. So if you want to like group, you want to like do comparison, we have the female and the male categories, the female and the male marital status in the genders in the data set. So now I want to like check the age distribution of age to female. Let me go back to this up and just do that in this up. So you are going to use this approximation sign kind of. So you are going to do RDS underscore female X. So you are going to have two groups, 0 and 1. You are going to see their heights. Yeah, and anything outside this shows the outliers. So now this is the minimum value. This is they call this bus plot 5 quantitative summaries. This is the minimum value. This is the 25%. This is the 50% percentile. This is the 75% percentile, and this is the maximum value. Then this is outliers. Yeah, so it's called five quantitative summaries. So that's what it does when you put dollars approximately, so like kind of dollar sign a categorical variable is going to give you this kind of plot. So if you want to make a scatter plot, okay, I know someone might be asking me, how do we make this same plot in ggplot? Using ggplot, right? You use ggplot. So what's our data? RDS, right? Our AES, you specify X equals X to be what? To be female X, comma, and Y equals age, right? Is it age? Yep, age. So plus geom box. So can you see? Still the same thing. Then you can start adding your athletics. So do you want to tell me that there is difference between this plot? I'm sorry, where's the plot? Do you want to tell me there is difference between this plot, this one, and this? No, there is no difference. It's just that the interfaces are different. Like what they interpret is the same. It's just that one is looking more sharp than the other. So no actual difference. So what if you want to plot a scatter plot? You want to like plot scatter plot. You use geom point. Yeah, geom point. So use geom point. After specifying your ggplot, RDS, X to be workload score, workload score, and Y to be GH score. I don't think I have that GH score. Let's see. GH score, and you run this, you print P. I know I don't have GH score. Let me just change it to mental health score. RDS. Let me just mental health score. Yeah. Yeah. And you run this, right? You're going to have this. So it's same as just like plotting, doing plots of X equals RDS workload and Y equals RDS mental score. It's same thing, but one just look more beautiful than the other. So you can now start adding your labs and all this. It's the same thing. So if you want to like plot your bar plot, how your bar plot work is that it works. Your bar plots like plot categorical variables against their frequencies. So now we create a kind of data called bandit. So you have this. We've created data frame. We have age in that variables, which is this category, and we have frequency in the variable, which is categorical too as well. Once you load this line of command, you are going to have this. And you see, this is the data frame structure. We have age and frequency. So once you go down, yeah, you might need Tibu actually, Tibu package. You might need Tibu package actually. So it depends. So I want us to build this ourselves. Let's see what happens. We have ggplot, right? Ggplot into brackets. What data are we working with? This is the data we're working with. What variable do you want to plot? AES. We want to plot age, which automatically this is X, right? Even if I did not, no, this is X, yeah. Even if I did not specify that is X, R we recognize it automatically as X because it comes first, and Y, which is frequency. So what are we adding? We are adding geom bar, right? If you run this thing geom bar, it's not going to work because there is a function, there is an argument in geom bar called start, and you have to specify identity before it can work. Why you have to specify identity is that it's plotting frequency against this. So that's why you have to specify identity. Let's see if we did not pull the frequency, will it work? Let's try something. So if you don't put the frequency, it's just going to do the count, and this doesn't really make sense. So that's why you have to like put the frequency and specify identity. So it's going to like plot the age category against the frequencies. So from there you can now start like adding your statistics. I want this color, I want that, and this, that, which we are trying to like do in this line. So that's what we are trying to do. So if you want to like make the chart a bit more complicated now, we had sex into the data frame structure called the data frame we created earlier. So we have sex. So you are going to have age, sex, and frequency, right? So now let's see what happens. Okay, let me clean this. So now let's run this line one by one. So we have the age, we have this. Okay, so what I just did, I just cleaned it while we wrote it into an object. So I just cleaned it so now let's try one after the other. Let's clean this few and let's do this. Let's see what happens. This is what happened now. This is what we have before. Okay, now think of it. If I add field to this and say sex, and you notice that this field, earlier. Okay, let's do something before we do this. If I pass this field outside sex, what does it? It does not do anything, right? It does not do anything, right? Because it's outside. If I earlier, we said field to be equals to red, right? Let's see. When I say field to be equals to red, outside in the geom plot, ggplot, nothing happened. Okay, let's do this. Let's copy this. Let's cut it away from here. So let's come to into this bar section and pass this argument here. Let's see what happens. Incoming. So when I pass it in this geom bar, right, what happened? It paints the whole bars to be red, right? So okay, ask yourself this question. If I move this away from here and pass it into this AES argument, what will happen? If I put red, it will still like color this, still like color it to be like red, right? That's what it does, right? If I like change this to like a variable name in my observation called sex, what will happen? So you are going to have like, it's going to like partition them into colors. Like male represents the frequency of male, while female represents the frequency of female. Like orange represents the frequency of female. So it's going to partition them by color. It's going to partition them by color. So if you pass this into AES, something funnest part is that this, what are you calling this? This geomat it takes AES too as well. I'm coming. Let me show what I'm saying. This too takes AES too as well. If I move this away from this place, if I move this away from here and pass it into this place, it should do the same thing. Yeah, it's going to do the same thing. It takes like AES too as well. It takes AES too as well. Another way you can do this too is that, okay, let's just leave that. So this is this, right? This is this. So I think there is something called position. Yeah, position. If you do dodge, this is field position. If you do dodge, I think it's dodge. Yeah, you are going to have them side by side. If you do dodge, you are going to have them side by side. If you specify dodge, so you can change the colors, move around the statistics like every other person, and it's going to work perfectly. So I think the last visualization we'll be talking today is what I call it is the pie chart. Yeah, is the pie chart. Yeah, the pie chart. So we have set of observation called slice. So we create them in a vector. We have this called labels, kind of labels. Yeah, kind of labels. Each labels is for each slice. Like each slice is for each label. Each slice for each label. So now, once you run this slice, you are going to have this. Okay. Now to make it make sense, you know we have our data frame called BTU, right? This, right? Okay. Now let's plot this pie ourselves and see what happened. So we need what observation are we working with? Okay, let's say we are working with RDS of frequency. No. We're working with BA RDS of frequency, right? Yeah, comma. Against what? Our label. What the label should be? It should be it should be against age, right? Age. Yes. So once you plot this, it plots the frequency against age. Yeah, you can plot these two against sex. Yeah, so well, this doesn't really make sense. So yeah, so this doesn't make sense because you have to like do some calculation before you can do this. So against what I plug it with against age, right? Yeah, so it's going to show you each cut, like each cut, and you know their portion of the pie that it takes. So this is a very clean one actually. So you can see that this group from 30 to 34 years has the larger frequency, like that, and you can interpret your plot. So any question before we move to lab section 3? We still have like about 29 minutes to 28 minutes. Any question before we move to lab 3? Hope you guys are with me, or am I just like, hope I'm not just talking alone.
We are with you.
Oh, okay. So since there is no question, we just have to move to lab 3 actually. So yeah. Section 3. So now, lab section 3, what we are going to talk about in lab section 3 is comparing means and linear regression. I don't think I'll be the one to. Linear regression might probably be next week. Let's just talk about comparing means. And when we talk about comparing means is hypothesis testing. Like try to like test hypothesis, making a fact and testing if the fact truly exists or not. That's what comparing means does. So we can all move to like section 3 actually. So we have different method of like different type of hypothesis testing and different approaches of hypothesis testing. So it depends on what we are trying to test. So we have one sample t-test. So what sample t-test does is that it compares a mean of a continuous distribution to a pre-specified mean. So now what I'm saying is that maybe in Ghana, they said the average height of children below 15 is let me just say 25 centimeter. That's very bad. Okay, let me just say 1.7 meter. Yeah, the average height, the mean height of children below 15 is 1.75 meter, right? Okay, now as a researcher, I'm now thinking that if Ghana's mean height of children below 15 years can be 1.75, does that claim like happens? Does it happen in Nigeria? I think since Ghana and Nigeria behave like approximately like they have the same kind of behavior, I think that can work. And I want to test if like the average, the mean age or the mean height of children in Nigeria under 15 is 1.75. So I've already have my pre-specified mean already. So how can I test that? It's for me to collect observation from the population, select random observation of children below that age, and calculate the mean to compare the mean against the pre-specified mean. So that's what that does. And one of the properties of this test is that it's a normal distribution test. So your data must be normally distributed. It must be normally distributed. So if you want to test an hypothesis, what I will advise everybody to first do is that you have to like do some kind of quantitative summary and visualizations to know if your data is actually distributed. But in the case that if the sample size you are working with is greater than 30, yeah, there is assumption called central limit theorem in statistics, where wherever if the sample size is large enough and the benchmark of large enough is 30, that's how they put it. When the sample size is large enough, the sampling distribution of the means tends to be normally distributed. Don't worry about those grammars. Once your observation is greater than 30, you can use like any parametric test, like one sample test, two sample tests, independent sample tests, even if they are not normally distributed. Yeah, that's what that does. So we have a question here. So Dr. Sam from Hoshin Town believes that citizens in his town consume calories differently during each celebration than on regular. That is, he believes that on each celebration, the citizen in the town consume more calories than on regular days. So how can we test this assumption using one sample t-test? So mean calories consumption on a regular day is this. This is 2,100 calories. That's mean consumption on a regular day, equals to this. From 100 sample, but like sampled people. He sampled 100 people. So he sampled 100 people. So that is the mean. So now, after sampling 100 people on each day, he calculated their mean consumption, like their calories consumption, and it's got an average like of 1,850 with standard deviation of 300. On a regular day, the mean consumption is this. So let me put comma here. And mean calories consumption from 100 samples on each day is 1,850 with a standard deviation of 300. So to conduct this hypothesis, if citizens in the community consume calories differently on each day compared to regular days, we have to specify our hypothesis, our H0. So most importantly, you have to know how to coin out your H0, which is the null hypothesis. Null hypothesis. Let me just put this null hypothesis, which always say that there is no significance difference in the calories consumed consumed on each days from regular days. So it depends on how you understand. You can just say you can also say that the mean calories consumed on each day is significantly not different from regular days, depending on how you know how to specify. Why your alternative says otherwise. Yeah. So your alternative, you say that there is significant difference. So this is called alternative hypothesis, right? So alternatives, yeah, hypothesis. So now we have to like simulate, since we don't have original data, we have to like simulate the data. So how do we simulate data? We use random normal, because we believe the data to be normal. So what is our n? Our n is 100, right? It takes set of arguments n. It takes mean. And this data we are simulating is for the each days. This data we are simulating is for the each days, because we've already have the mean for our we've already have the mean for regular days, right? Which is 2,100 calories. So now the mean is 1850 and standard deviation equals 300. So once you run this line of code, you're going to see it's going to generate some numbers. Yeah, these are random numbers. It's going to generate some numbers. So that's what we do. We try to like simulate data sets, observations, data points for each. So then we write it into each. So to test your hypothesis testing, to test your hypothesis, one sample hypothesis, what you have to do is that you use t dot test. So you pass each. It takes mu, because this hypothesis, we are testing this hypothesis against the mean, called mean, yeah, against the mean. That is like widely known as mu, against the population mean, which is mu. So when you say m equals 21 and 2,100, so once you run this line of code, you are going to have this. The test statistics is negative 8.7945. So the degree of freedom is 99. The degree of freedom is n minus 1. That is the number of samples minus 1. And we have 100 samples. That's minus 1. This is obtained by how will I say it? Okay, the formula for this is x minus mu divided by x standard deviation divided by root n. That's the formula. If you want to like compute it manually, you have to like search that online. So what we are mostly like trying to interpret here is that we are trying to like interpret the p-values, because these p-values is what we use to like make decisions. So be careful enough, depending on your level of significance. If your level of significance is 0.05, so the thumb rule is that you reject the p-value if the probability value is lesser than level of significance. So if we are using 0.05 in this case, the question you have to ask yourself is that, is this p-value lesser than that 0.05? So can someone please just unmute and tell us if this p-value is lesser than 0.05?
I think it's higher.
This is higher than 0.05, right?
Yeah.
I think
Less.
it's low. It's
Okay.
less.
Okay, thank you.
It's
So
less.
now let's do something. I copy this value, right? Let me copy this value. I'm coming. Let me just copy this value. Okay. And come here. I just want to make use of that. Greater than 0.05. So we want to check if this value is greater than 0.05. Sorry. What's happening? Okay. Pause. This is not greater than 0.05. So definitely it's lesser than 0.05, not is it greater than 0.05 false. So it's lesser than 0.05. So we tend to like reject our null hypothesis. Our null hypothesis, which is that since it is lesser than 0.05, we reject the null hypothesis, and you state your conclusion like, oh, we did not have sufficient evidence. Okay. Due to insufficient evidence, we reject the null hypothesis and conclude that the mean calories consumed on each day is significantly different from the mean calories consumed on regular days. That's how to coil the interpretation. Due to we reject the null hypothesis due to like insufficient like evidence or the kind of stuff, or you can say we reject the null hypothesis and conclude that there is significant difference in the mean calories consumed on each days compared to regular days, or the mean calories consumed on each days is significantly different from the one consumed on regular days. So it's going to give us a 95% confidence interval as well. So 95% confidence interval is a range of values. Yeah, this is a range of values which we believe that our true parameter mu lies with. That is the actual mean calories, the actual mean calories consumed on each days, like where it falls, and we believe that falls between this and this. So that falls between this and this. So that's that. So do we reject the null hypothesis? Do you conclude that the calories consumed on each days are different on average from the calories consumed on regular days? Yes. So now, these are another practical, right? Okay, these are examples. Before we go to PAT test, let's see if I can walk you through this example. So you are the new CMD at Lagos Hospital, and you asked all 187 resident doctors how many hours they worked last week, and you computed a mean. You obtained a mean of 71.6 hours and a standard deviation of 16.9 hours. Determine whether the calculated mean is significantly different from 40 hours. So now, since we don't have an actual data, we want to like simulate the scenario. So we have let's just say this is hours, right? Let's just use hours, for example, and say, okay, random number, n observation 187, mean of what? Mean of 71.6 and standard deviation of 1. Something is wrong. Okay, I can see this is equals to, yep. So we have our observation for hours, right? These are the observations. So we want to test now. Tests.
I'm sorry, the standard deviation is written 16.9, but you wrote 1. Should we use 1 also?
Oh, no, sorry.
Right, 16.9.
Yeah, sorry. I'm sorry.
Okay.
Hours, yeah, and mu equals 40, right? 40, yeah. So you are going to have this. So now, can someone just unmute and interpret this result for us? The question you want to ask yourself is that, do we reject the null hypothesis? And do we conclude that the hours the hours worked by the resident doctors on average is greater than 40 hours per week? So can anybody help us with that based on this output?
Yes. So I would say that in this case too, we also reject the null, because the null hypothesis, because there is a difference. Here we have a mean that is higher than 40 hours per week.
How do you conclude that there is difference?
Because the p-value is less than 0.05.
Exactly. So do you reject the null hypothesis or you accept the null hypothesis? No, we don't say
Reject the null.
okay. You don't say you accept the null hypothesis. If you did not reject the null hypothesis, you say we fail to reject the null hypothesis. So I take that back. We don't accept the null hypothesis.
Okay.
So do you reject or you fail to reject?
Reject.
Oh, okay. Thank you very much. So that's it. So now I have to point something. We have directional test and we have one t-test and two t-test. So this is just like a plus. Okay, now this we are checking if there is if the hours they work is significantly different from the standard hours, which is 40 hours, right? If we say something is significantly different, that is the hours worked is not equals to 40 hours. When we say something is not equal to 40 hours, it can be greater than 40 hours or lesser than 40 hours, right? So that is where one t-test come. What if they tell you that we want to test if the hours they work is greater than 40 hours? Because this will just tell you that the hours they work is significantly different from 40 hours. It does not tell you if they work more hours or work less hours on average. So that is where one t-test comes in. So now let's try to like integrate that into what we've done. So this is same thing. You just have to just come and write alternative. Because in this case, let me come back to this place and explain something. In this case, we say there is significance difference, right, in the calories consumed on each days from regular days, right? Let me just say that upper t-test, like one sample, like one t-test, we tell you that the hours worked on each days is greater. The calories consumed on each days is greater than regular days. If it's like upper tilt, if it's lower tilt, it's going to tell you that the calories consumed on each days is lesser than regular days. I don't know if you get what I'm saying. That's different between like two tilt tests and one tilt test, depending on what hypothesis you are trying to test. So let's use this resident doctors now. We want to now check if the hours they work is greater than the standard hours, not that if it's significantly different from 40. We want to actually know if they work more hours or work lesser hours. So alternative, you have to specify I think is alternative. Okay, yeah. You have to, because we want to check if the hours they work is greater than the standard hours. So that's greater. So once you specify your alternative to be greater, then you calculate the same thing. So from this point, you can reject your null hypothesis and say that they actually work more hours than 40. Because your hypothesis will be null hypothesis. Let me just use A0 because the hours of work by the residents doctors is not significantly greater than 40 hours of standard work. Yeah, when we mean not greater, that is lesser than or equals to. Yeah, and the alternative, which is A1 or H1 or HA, state that is significantly greater. So that's what we want to test. So once you run this with this p-value, you reject your null hypothesis and conclude that the hours they actually work, this gives you if they work more hours or lesser hours. If they work more hours, and since we are rejecting the null hypothesis, it says that the hours of work by the residents doctors is significantly greater than the 40 hours of standard time, work time. Okay, what if you want to test if the hours work by the resident doctor is lesser than the hours the standard time? So this hypothesis will change to less, right? Less, right? This will change to is not less, right? When it's not less, this alternative is going to change to greater than or equals to. This is going to change to less, right? Okay, let's see. You are going to change this from alternative to be greater than to be less. Yeah, let's see. So can someone just omit and interpret this result for us based on the p-value?
So I think we failed to reject the null because the p-value is greater than 0.05.
Exactly. So can you see what the difference between two tail tests and one tail test? Two tail tests will tell you if they are not significant with the test parameter, the test population mean. But this is going to tell you, is it greater or is it lesser? It's going to tell you the actual direction of the how the actual direction, if it's lesser, if it's greater or lesser. Yeah. So that's the difference. I just have to just point that to everyone. So now we have paired t-test. You know, paired t-test. When we talk about paired t-test, let me just like summarize it like in just, it's just testing hypothesis between two groups. But you have to note it's not two groups, it's just a group, but at is it a 2-point interval. Maybe we are trying to, okay, I am employed as a new teacher to teach R in a class, in a school. So when I started, when I want to teach R, I gave the students a test on my first day before teaching them to like assess their scores, to know if they, to assess their knowledge in R skill. So after 6 months of teaching them, I gave them that same question to see their scores behavior, and I want to compare if my teaching actually increased their knowledge. Can you see that it's like different time interval, right? It's different time interval, same students but different time interval. Same students but different time interval. Okay, let's assume let's use the resident doctor case now. Maybe after doing the one sampling test, we observed that larger proportion of them, they work lesser hours than the standard time. Okay, we now say, oh, if you work more hours for the next 1 year, anybody that work more hours get a bonus. And after that 1 year, we still do the calculation and see the amount of hours, the number of hours they work. We will now want to compare if that bonus initiative changes their behavior towards work. You know, same resident doctors, but at different point interval. Same observation, same group of people at different point interval. It can be same observation, maybe at different treatment. Maybe you have someone is using drug A before. Okay, now some people that have like high blood pressure before, like set of patient that have high blood pressure. So before giving them a particular intervention, we calculate their BPs, and after giving them the intervention for 6 months, we calculate the same BPs and check if there is a significant difference between before giving them the BP and after giving them the BP. I don't know if you understand. Do you have any question regarding what I just like explained? Same group of people, they are just same group, but at different interval or different intervention. So is there any question? Okay, I'm going to take that as no. So now let's run this example. So you are the new CMD at Lagos Hospital, and you ask all 187 resident doctors how many hours they worked last week. You calculated the mean and you obtain 71.6 hours and the standard deviation of 16.9 hours. Okay, now after 12 weeks, you have everyone 12 weeks. You ask everyone how many hours they've worked in last week, and obtain 63.8 mean. You obtain a mean of 63.8 hours and a standard deviation of 17.3 hours. So you want to know if your hiring practice changes the number of resident doctors' hours, like the hours of work, the hours in which they work. That is in between. If the hiring process, like practice, changes the numbers at which they work. So you have to make an hypothesis first. H not to be like maybe kind of the number of hours they work is not the number of hours they worked in the last 12 weeks is not significantly different between the hours of the work they work now. You can just do like how would I put this, week 0 and week 12. That is the hours, how would I put it, there is no significant difference between the number of hours worked in week 0 against week 12. That is, the mean hours worked in week 0 is significantly not different from week 12. Why the alternative say the mean hours worked in week 0 is significantly different from week 12. That's how to specify that. So now, we have to simulate because we don't have the actual data. So we simulate this just the same way we've done the random sample. So now, what we have to do is that, so we have to come here. This is 2 tests. We are not checking if week 0 is greater than week 2. No, we just want to check if there's significant difference. So once we run this line of code, what's the only difference between this is that, previously we were using test.t, right? We just only specify week 0, let me just say week 0, and we put mu to be this, to be the value, right? To be the value. Then we run that. But in this case, we have to add another argument because we have two data points, right? We have 2 variables, week 0 and week 12. So test dot week 0, comma, which is like x, week 12, comma, you have to specify period equals true. Period equals true. So you might not even put an alternative because at default, I recognize the alternative to be 2-sided, if otherwise. So if you run this line of code, you are going to have this. So can someone just unmute and interpret our result? Do we reject the null hypothesis that the hour works in week 0 is different from week 12, or is not different? Do we reject the null hypothesis? Can someone just like interpret this for us?
Yes, we reject the null because the p-value is less than 0.05.
0.05. Okay, now. So now, what you just have to just do is that if you want to check which one is greater, you can just come here and just say greater test. You see if it's greater or less. Then you interpret depending on the question you are trying to ask. So we are unable to like finish this section today, but I think ideally we should finish this section. So I think next week I might just run through the rest of this section before moving to linear regression. So thank you very much for like attending to this section. This class is a 2-hour class, and we've come to the end of this section today. So before going, do you have any question?